Hi everyone, this is Ali Raza with another video. So, in this one, we are going to look at the calling convention, and I believe we need to look at the calling convention before even programming assembly language because this is actually the most common source of confusion because if people don't know about calling convention then they get confused like how are people knowing which registers to use, how do they know where the output is and all sorts of stuff. So I believe that we need to like look at the calling convention. Alright, so let's get started. What we will cover is that we will see the x86 calling convention and the Linux calling convention. Primarily, we are interested in the x86 variant, but we will also see the Linux convention because you know what, it's no harm seeing it. So we will see both of them. Okay, so what actually is a calling convention? So, in simple words, you can think of it as a way of standardizing so that you know where things are, especially when it comes to registers, because people often get confused where to pass things or where to get the results. So column convention actually helps in that regard, and this is what we have. It's the calling convention. And why do we need it? So I think everyone by now, those who are technical, they know that standardizing things is actually the way to go, because if you don't have any standard and in assembly if you don't have any convention, then what will happen is that everyone will start using their own convention, and then eventually what will happen is that every program will look and behave in a certain different way, and that way is related with how the registers are used for input and for output. So calling convention is actually a way of standardizing the inputs and outputs. In a nutshell, this is what it is. So when you have a calling convention, you know exactly which registers to use when you are passing the input, and when to use the stack, and which registers to use when you are getting the output. This actually ensures compatibility and interoperability, right? Because if you have different code pieces of code written by different people, being like those are generated by different compilers, and you know that okay, if this program is using a certain standard or calling convention, then you know that okay, these registers are being used for input, these registers are being used for output, we have this and we have that. So that actually clears a lot of confusion for us, for the operator, to say, like for the person who's looking at the code or who's programming it. Okay, so for x86 we actually have three calling conventions, and the first one is that std call, the second one is c decl or the c declaration, and the third one is fast call. So we will look at them individually. I will also show you piece of code, but I would encourage you to just try to understand the whole idea, and not to get confused as to what the code is actually doing, like line by line, because actually this is not our end goal. We haven't even started programming in the assembly language. So yeah, don't get confused when you see the code. Alright, so std call is actually very common in the Win API, the Windows API, and the Windows System Call. So anytime you actually disassemble code in the Windows, and if that code uses Windows API, then you will see that in the disassembly you will find this std call a lot, and by that you should know that it uses the std call convention. And when it uses this convention, there are certain things that you need to remember. The first one is that the parameters are passed in right to left order. Now what do I mean by right to left order? So suppose you have a function, let's say add, and it takes two parameters. Number one, the first one is a, the second one is b. And when I say right to left order, uh, that means that if we are passing those parameters in assembly, we will pass them in a reverse order. So we will first pass the b parameter, then we will first pass the a parameter. So this is not usual because in high level languages we actually pass them as is, in the same order that they are described in the definition. But here we are passing them in the reverse order. So the last one, the second last one, and so on. And then the third point says that the Kali or the function is responsible for stack cleanup. We haven't actually looked at stack, what the stack frame is, what do you mean by stack cleanup, but in the next video I will try to cover everything about stack, what stack is, what stack frame is, how it grows, how do we clean it up, different registers that are related to it, the function epilogue and the prologue, all these steps. So you don't need to worry about that in this video. Alright, and then we have that return value. So the return value, whatever output the function gives, you actually get that in the EAX register. And you can see that this is actually very helpful, very important, because if you know that the code is using certain convention, then you don't need to juggle around. You know that okay, if a function is executing, the return value will be stored in the EAX register. And then finally we have registers that are preserved, i.e. their values are not changed if the function is executed, and some that are changed or will change if the function executes. So here we have EBX, ESI, EDI, and ABP. ABP is the base pointer for stacks. Again, we haven't looked at stacks, so you don't need to worry. And in that case, I think ABP will not be changed. While EX, ECX, and EDX, they can change. So yeah. And this is an example. What you see on the right hand side is just how it will look in assembly. It doesn't necessarily mean that this will look exactly like it. And again, you don't need to worry if you don't understand any of the code that is written on the right side, because you just need to like get an overall idea of how actually things are, how they look. So if you see on the left side, you have a standard C code. What it does is that it has a function called multiply that takes a and b, and then what it returns is the product of it. So if you look at the assembly code, we actually haven't started programming in it, but if you look at it, you can see that the order is right to left. So we start from b, then a. So in the comments say push the second argument, push the first argument, and then call the function. So this is what we mean by right to left. That means reverse order. And then the multiply function itself is actually the assembly way of doing the multiplication. You don't need to worry about that part, because the part that is here is important for us. We just need to know that the order is passed in the right to left order. Alright, and yeah, so this was STD call. Then we have C declaration. I think this is self-explanatory because it's a default calling convention for C and C++ programs. And again, parameters are pushed onto the stack from right to left order, and this time the caller is responsible for cleaning up the stack. When we say caller is responsible or callee is responsible, uh, what that means is that if someone or something is calling a function, and we say that callee is the responsible, then that means that the callee has to make sure that stack is in the same order that it was before it called the function, right? So it shouldn't do something weird with it, such that when the function executes, it's in a different state. So that's what we say responsible for cleaning up the stack, making sure that it's in its old state before the function was called or executed. And again, the return value is stored in the EAX register. same as the standard call, STD call, and the registers are also same here as well: EBX, ESI, ADI, and EBP. The example is going to be same, so I haven't included it because I just want you to be aware of the calling conventions. Examples are mostly same for these conventions. And then finally for the x86 we have fast call, and this one is actually what you have in the x86 environment. So when you are writing x86 assembly, you will see that this convention is being used. This convention is used in the x86 environment, and things are a little different here. So if you have, suppose you have a function that takes 4 arguments, and the function is called max, for example, and you pass it 4 arguments: first number, second number, third number, and fourth number. And if we think of it in terms of assembly and the fast call convention, then the first 2 arguments, the first number and second number, those will be passed to the registers themselves. So here those registers will be ECX and EDX, while the remaining arguments, those will be passed on this onto the stacks. And I'm sorry, I think I messed up the order. It's going to be right to left. So the uh, last argument is going to go to the ECX, the second last argument is going to go to the ADX, and then the rest before that are going to be pushed onto the stack, but in reverse order, because the order is right to left, not left to right. And Collie is responsible for cleaning up the stack. You get your result in the EAX register, and then again the registers are same. Those are preserved: EBX, ESI, EDI, and EBP, and then EAX, ECX, and ADX are not. Alright, so this is an example for fast call. You can see that we have a function on the left side which is add, and it takes 2 numbers, A and B, returns the addition of it. So if you see the right side, don't worry if you don't understand much of it. You will see that we push the second argument first and then the first argument. So we push 5, and then 5 is actually what is the argument for B, and then we push 3, which is the argument for A. We then call the function, and then the line below it, don't worry about it. And then we have the add function itself. It does the stuff and then gives us the result, and that's it. So you just need to know where you are going to get the output, what parameters are going to be passed to the registers, and how the stack is going to be used. And that's the important part. Alright, and then we are actually looking at the Linux convention, although it's optional. But in Linux we have 2 ways. So for 32-bit Linux we have the i386 calling convention, and for the 64-bit we have the system v AMD64 ABI. And if you want to know more about ABI, I encourage you to go to Google and have a look at what ABI is. That will help you a lot. For the 32-bit i386 calling convention, the function parameters are pushed onto the stack from right to left, reverse order, and the caller is responsible for cleaning up the stack, and the return value is stored in EX. You will see that in almost every convention that we have seen, the return value is almost always stored in the EX. And then you have something new which says that EBX, ESI, EDI, and EBP registers are callee saved, while EAX, ECX, and ADX are caller saved. What do we mean by callee saved and caller saved? When we say callee saved, that means that EBX, ESI, EDI, and EBP, the callee needs to make sure that when it started to modify them, it saves their previous state somewhere, such that when it's done doing its thing, executing any stuff that it wants to, and that it actually restores these registers to their previous state. Because we know that this is not the only function that is going to use these registers. Maybe something else is also going to use them. So the callee needs to make sure that their state is restored once it's done with the execution. And this is what we mean by callee saved. So callee needs to make sure that the state is not altered, so it doesn't like execute, and then when we come back from the function and we like get to know that okay, EBX and ASID and EBP, they are changed. It shouldn't happen. They should be in their old state, although it can change, but it should somewhere store the previous state, and then once it's done, restore the previous state, and then continue the execution. And for EX, ECX and EDX, the caller needs to make sure that their state is same. So whatever happens, it needs to save the state, and things happen, and then it needs to restore the state to make sure that it's not altered in the end. And I have actually added like two small lines below it so you can read them as well. And for system V AMD64 ABI, I think this is the most interesting one, personally my favorite. So the first six arguments are passed to the following registers. It's RDI, RSI, RDX, RCX, R8 and R9. The first six arguments. If you have a function that has six arguments, those will go into these registers. And one interesting thing, if you have floating point arguments, now suppose those are not integers, those are in a floating point, uh, if any, so those won't be passed to the like normal registers, they will be passed to the FPU registers. So I think we saw them in our first video. Those are XMM0 to XMM7, so you are going to use those registers to actually store the arguments if they are in floating point. And then you have something new here as well, which says this stack must be aligned to a 16 baud boundary. I think you will understand this once we actually reach stacks, because then you will know that what is a stack alignment, why we align stacks, and there are certain bytes that you have to make sure are available. In, for example, in Windows we have something called shadow space, and that shadow space we need to make sure that we have that available on the stack. And here we have the 16 byte alignment, and we will see all of that in the video when we discuss stacks. Alright, then caller is responsible, uh, general stuff. Again, RLX is used for the return value, so whatever output you have. And then you have these registers that the callee needs to make sure are preserved, and then some registers that the caller needs to make sure are preserved. Alright, so I think this was all about calling conventions. I hope this was not overwhelming, because again, calling conventions are not easy, and you don't need to remember all of that. What I would suggest is that when you start programming in assembly, or when you start looking at it, disassembled code, you should just reference things, because you don't like remember these things at once. You remember them over time. So reference them and look at them. Look at the conventions, like if the code is using a certain conventions, then look at the points for that convention, and you will hopefully understand. So what we will do is that in the next video we will try to cover stack, because I feel like stack is most important. And after this video we need to make sure that we have a general understanding, a good understanding of stack and all the concepts that are related to it, because again, without it a lot of confusions will arise. So I will see you all in the next video. Until then, thank you very much.